Okay, we're moving now to Chapter 8, Correlation and Regression. And basically what we're going to be doing here in Chapter 8 is dealing with relationship between two numeric variables. I'll just mention as a caveat that there are correlational measures of relationship between variables at different levels of measure, but the overwhelming use of correlation is to assess relationship between numeric variables. So let me just recap a little bit on relationship. You know, in Chapter 6 we defined relationship, and we basically said when certain values of one variable tend to occur more often with certain or particular values of another variable, we've got relationship. So that if, for instance, people in different regions of the country respond differently on some question, then we've got relationship. At the end of Chapter 7, we expanded the notion of relationship to look at directional relationship, in particular at directional relationship between two categorical variables. And here, rather than simply saying certain values tend to go with certain other values, now we're able to introduce the notion of direction. We're able to say that as one variable goes up or down, the other tends to go up or down. So in Chapter 8, we're expanding the idea of relationship to two numeric variables. I mean, and we're going to be able to be more precise. We're really building on the notion of directional relationship. So rather than just saying as one goes up, the other, for instance, goes up, because we're dealing with numeric variables, we're going to be able to say as one variable goes up by some given amount, for instance, as one variable goes up by 1 unit, the other variable is predicted to go up by a particular amount. So it's not just direction, but we're able to be more precise and to speak numerically and to talk about the particular amount of change that is predicted as a first variable that changes by some amount. A key measure in the first half of Chapter 8, and indeed really our key measure of relationship between two numeric variables, is Pearson's R. Pearson's R measures the degree of linear relationship between two interval ratio level variables, or we can just as well say pragmatically between two numeric variables. And what do we mean by linear relationship or linear association? It's association that can be described by a straight line. So Pearson's R is measuring the degree of straight line relationship between two variables, and we'll see soon what that means. Pearson's R is a workhorse measure of relationship between numeric variables, and that's a great advantage. So that, for instance, for relationship between two ordinal level categorical variables, there are many different variables that compete with one another. And no relationship, at least that I know of, has risen to the fore to say this is the key and best measure. So that is indeed what Pearson's R is for linear relationship between numeric variables. So correlation between two numeric variables can be either positive or negative, and we'll talk about some other patterns of relationship too, but for the present, let's keep things straightforward. Positive correlation, I mean, it's carrying the same basic meaning as positive relationship. So values are changing in the same direction. I just did give a caveat to say soon we'll see that, I mean, there's more precision than this, and that we're able to say as one variable changes by a given amount, the other is predicted to change by some given amount. But it's clearly a key idea in positive correlation is that values change in the same direction. Another key idea in positive correlation is that similar values tend to occur together. So let me take a look at this scatter plot here in the lower right of the slide. So I mean a scatter plot conveys visually relationship or lack thereof between two numeric variables. Correlation in meaning is very similar to relationship. So I'll say also that, and perhaps more specifically one could say, I mean, a scatter plot conveys the correlation between two numeric variables. It can convey correlation or, more broadly, relationship. So let's take a look here at this scatter plot. And this scatter plot is depicting relationship between two variables, distance jumped in the long jump and height jumped in the high jump. And each dot conveys an individual's score on these two variables. So I'm moving to this particular dot. This person's high jump height was about 5 3/4 feet, tracing over to the y-axis, and this person long jumped, perhaps 13.5 feet. And you can see the slope of the scatter plot from lower left to upper right. And when that scatter plot has this positive slope, that's conveying positive relationship to you. It's conveying the values changing in the same direction. As long jump goes up, high jump height tends to go up. So now what do I mean by similar values tend to occur together? Let's focus on some different areas of the scatter plot. So in the lower left, you've got dots occurring in the lower left. And these dots, or we can call them markers, are conveying a given individual's performance on both of these variables. So let's look at this individual's performance here. I'm looking at a given dot. This individual's jumping up just a little bit over 10 feet in the long jump. So relatively speaking, this is a low distance, a short distance. This person is low in the long jump, which is to say they're on the left side of the x-axis. And similarly, this person's high jump height here is under 4 feet. They are at towards the bottom of the y-axis, so they are low in high jump. So this particular person's long jump and high jump values are both low. And so the idea here is you see a congregation of dots in this lower left area of the scatter plot. So those are people who are low in both long jump and high jump. So similar values are going together, lows with lows. And if we come up to the upper right part of the scatter plot, you're seeing individuals who are high in the long jump, which is to say to the right on the x-axis, and they are also high in the high jump. They're towards the top of the y-axis. So we have illustrated in this area highs in long jump going with highs in high jump. Again, the notion of similar values going together. I mean, we can extend this to the middle area of the scatter plot too. Here are middles going with middles. So similar values are going together. Now just notice, for instance, that there are no dots in the upper left area of the scatter plot. So the upper left area would be low in the long jump. I guess I should say short in the long jump, but low versus high. So low in the long jump, on the other hand, high in the high jump. So if we had low in the long jump and high in the high jump going together, that would be a case of dissimilar values going together. But notice there are no dots here. And similarly, here is another area where if there was a dot, that would be an example of dissimilar values going together, but there are none. So that's why in positive correlation, a key idea is when there is positive correlation, it's conveying to you similar values tending to occur together. Highs with highs and lows with lows. And then the other, key idea in positive correlation, as I mentioned, is this lower left to upper right, which is to say the upward slant of the dots in the scatter plot. The scatter plot on this slide is conveying a negative correlation between two variables, and this is, has the same basic meaning as negative relationship. So you can see that the slant of the dots is from upper left to lower right. So we can say the slant of the dots is downward. And when you get this upper left to lower right slant, that's negative correlation, and values are changing in opposite directions. So let's see what happens as time in the 50 meters goes up. What happens to high jump height? Well, as we go from left to right, which is to say up, in 50 meter times, you can see the pattern is for height jumped to come down. So as 50 meter time goes up, high jump height comes down. So the values are changing in opposite directions. You can talk about this in different ways, and I don't want to take up too much time doing it, but you could say as 50 meter time goes down, high jump height goes up. Or for instance, another way to say it, you could look at it the other way. You could say as high jump height goes up, times in the 50 meters tend to go down. So as we're going up here, we're moving from right to left here. And so values changing in opposite directions, that's a key notion of negative correlation. And then we have this corresponding idea of dissimilar values tending to occur together. So let's look at this area of the scatter plot. Here are folks who are low in 50 meter time and high in high jump height. So they're low in the 50 meter and high in the high jump. These are dissimilar values occurring together. And similarly down in this quadrant or area, we have high in the 50 occurring with low in the high jump. So this particular person, for instance, has a high 50 meter time and a low high jump height. So dissimilar values are occurring together. Now I'll probably mix you up. In both positive and negative correlation, you don't see these patterns in the middle values. So I suppose it's the case that the middles on one are tending to occur with the middles on the other, but don't focus on that. The key idea is illustrated by the highs going with the lows, or we can say the lows going with the highs, that the dissimilar values are occurring together. Well, I know the last thing you probably want to hear about is a formula, but here's the formula for R. Let's take a look at it and help you gain some understanding of it. So notice that z-scores are involved in the formula for R, and I'll mention this is the formula for R presented in this text. You can find different formulas for it elsewhere. But we've got z-score on x and z-score on y. So how do you calculate R? And so I guess I want to say, recall that z-score on y, for instance, is telling you how many standard deviations above or below the mean a given case is on y. And z-score on x is doing that for x. So, to calculate r, go back to chapter 5 and you'd look at your z-score formulas, and you would transform scores on both variables into z-scores. Scores then are expressing for each case for each of the two variables how many standard deviations above or below the mean. And then the summation sign tells you for each case multiply the z-score on x times the z-score on y. So that's presented here. Let's focus on the summation sign. So the summation sign is telling you, and it's step 3, after you've multiplied the z-score on x times the z-score on y and figured out the product for each case, then you're going to sum those products. And finally, the last step is to divide by the sample size minus 1. So let's take a look at a calculation example. Here's our formula. Our example is going to calculate the correlation between family visits and depression score, say of families at a nursing home. And notice we've got two numeric variables, and both of these variables are at the interval ratio level of measurement or very close. So here are, well, here's our 8 cases, our 8 families, and here's our family visit scores, and here are our depression scores. So then what's calculated in the 4th and 5th columns are z-scores. So here is the z-score, for instance, for visits for family 1. So notice that this family was very, very slightly above the mean. I mean, the z-score of 0.17 conveys 0.17 standard deviations above the mean. And then also let's look at depression, and it's the case that their score was slightly above the mean for depression. And in the rightmost column, we have the product of the two z-scores. So we multiply the z-score on x times the z-score on y, and we calculate the product of those z-scores. Let's take a look, for instance, at family 4. I mean, so intuitively, I mean, eyeball the number of visits. You can see that the number of visits is the lowest among the 8 families, so that's a clue to you. They're going to have a very low z-score on visits, and yes, indeed, they do have the lowest z-score of all of the families on visits, about 1.5 standard deviations below the mean. Let's look at their depression score, and their depression score is actually the highest of the depression scores, so that's a signal to you they're going to have a high z-score on depression, and indeed they do. Their z-score on depression is almost 1.5 standard deviations above the mean. And then you can see the calculation of the product. So minus 1.56 times 1.44 equals minus 2.25. Third step, the summation step, sums the product of the z-scores. And the z-scores sum to minus 4.15. The final step is the division by n minus 1. So we had 8 cases, so n minus 1 is going to compute to 7. So minus 4.15 divided by 7 equals minus 0.592. So in this example, R equals minus 0.592. R is the symbol for Pearson's correlation coefficient. So in this example, we have a negative correlation between family visits and depression scores. At the risk of being repetitive, let me say that this is conveying to us as family visits go up, depression scores tend to go down. And it's also conveying dissimilars going together. So that's the notion that where family visits are low, depression tends to be high. Where family visits are high, depression tends to be low. So this slide is presenting the correlation between family visits and depression visually. I mean, that's what scatter plots do. And the slant is indeed from upper left to lower right. And the correlation, as already stated here, is a -1, minus 0.592. Now, I just want to give you some intuition, if you will, into the formula. So let's think about positive correlation. Recall, in positive correlation, similar scores tend to go together. So that, for instance, that's conveying to us that if there's a positive z-score on one variable, there will very likely be a positive z-score on the other. That's the notion of highs going with highs. And positive correlation is also conveying to us that negative z-scores will tend to occur together. If the case is low on x, it's very likely going to be low on y. So, in positive correlation, you're going to have pairing most often of positives with positives. Positive z-scores with positive z-scores. And when we multiply z-score on x times z-score on y, we're going to get, for those cases, a positive times a positive. And you know from early math that a positive times a positive equals a positive. And then similarly, the negatives go together, so we're going to get a pairing of the negative z-scores most often. And a negative times a negative yields also a positive. So positive correlation, I mean, the formula churns out a positive value intuitively because positives are going with the positives and the negatives with the negatives, and the cross products are most often positive, so you sum them up to get a positive value, and therefore a positive R, which is to say an R greater than 0. And things are just the opposite with negative correlation. So negative correlation is conveying to you that, so to speak, opposites are going together. Highs on x are most often paired with lows on y, so I'll say positives on x are most often paired with negatives on y, and similarly, or correspondingly, negatives on x are most often paired with positives on y. And in either of these situations, you're going to get a negative cross product. Positive times a negative equals a negative, and in this example, the negative times the positive yields the negative. And so this is the notion here that when the multiplication of the z-scores produces negatives, I mean, that yields the negative value of r. So this is how the formula, in essence, does its thing. And I think we'll just leave it right there.